Hello, everyone. I will start a new video, but today I will set a timer for myself, just so that I don't spend too much time. So yeah, I would prefer to spend 40 minutes on the problem and then 30 minutes more on sharing ML system design content than just hour and a half on the problem as in the last few days. Okay, so let's start. Today's problem is, as you might have seen, shortest Subarray sum with at least k. So let's see. Given an integer array nums and an integer k, signature nums, which is a list of integers, and k, which is an integer. The length we are returning, so the length of the shortest non-empty subarray of nums with a sum of at least k. Okay. So let's do tests, and I will mention challenges. I will just say that maybe a challenge will be negative numbers. But let's see. So first let's try positive numbers. So let's do 1, 2, 3, 6. And then 1. And let's say the k is 5. So that would result in 1, because this is at least k. This number is at least k by itself. And but all of those are longer, so this is the shortest possible one. Okay. Now do so. Okay, let's say 4 minus 3, 7. 5 minus 3, 7, 1. And we want to get 9. In such scenario, we need to choose the first 3 elements. 3 elements. Okay. So let's try to think about the solution. I'm thinking about 2 pointers, and I don't see why this is not working, wouldn't work. So let's say our invariant will be that between the 2 pointers, pointing at the elements of the array inclusive, we will always try to have at least our sum. This might not happen, right? So can we have a negative number, by the way? Maybe just for the sake of it, 1, 2, 3, and -1, and it will be 1. That will be the answer. So we can easily get this sum. But what I'm worried about, right? Okay, connection reestablished. Could you please work? Thank you. So what I'm worried is, let's say that we start with something like -10, and then we do 1, 2, 0, and our goal is to get to 3. So we know that the answer here is 2, but if we just do an increasingly large window, we will never get to the correct level. So how do we know how to grow and shrink our window, right? Because the greedy approach might not work. It can be something like so let's say we have -5 and 6 here, and we are targeting 4, right? So for example, let's say we are growing our window further and further. We have grown it here. Now we need to choose, what do we do? Do we remove this number, or do we add this number? So if we remove this number, if we just always do whatever grows our sum, can we guarantee that we will get the biggest possible sum? Because it's okay, let's say we are here, right? We have grown to this window. Then we know that either we can decrease by -5 or increase by 10. So we increase by 10 and we get this window. And then we can choose either we decrease by 1 or decrease by -5. And then we will choose decreasing by 1, right? So we will never get to 4 if we just use this greedy logic of always doing whatever grows our window sum. So how can we go about this? We should also search over such windows. Okay, let me start with a simple solution, and then I will try to figure out something better. So brute force will be first calculate prefix sum, second for each prefix sum find what's the smallest. For each prefix sum, find the for each I and j, find the sum between and choose the smallest. So essentially it's O of n squared, and even more brute force solution would have been to just choose all the possible combinations of I and j, and then summing the numbers between those and getting to off and cubed solution. Force ish, the most brute force one. Brute force, calculate all possible sums in off and cubed. So brute force ish, we do that in off and squared, and then it's relatively simple. Then the question becomes how to find. Can we use this prefix sum to reduce the amount of calculations that we need to do? So we also know the target, right? So for each element of prefix sum, we need to find whether there is an element of a target value. So for example, let me just calculate the prefix sum here, right? So the prefix sum will be minus 10, and then it will be minus 9, and then it will be minus 7, and then minus 7 minus 12, and then minus 6, right? So we know that for each of those elements, we need to find an element that will be sufficiently big so that when we do this element minus some other element, we will actually get to the number that we want to get. Oh, actually the answer here will be 1, obviously. I missed that because this is already enough. But if we did something like minus 1 and 2, that would have been more interesting. So here we just do minus 6 and minus 12. Maybe let me do both the examples here. So here it will be 1, but if we do minus 1 and 2, then it will be 4. Okay, now we have calculated. Let me copy it in the solution so that we will keep our ideation there. Okay, so we are trying to get this. Then we need to find for each solution, for each possible prefix sum, we need to find whether there is an element smaller, such that this element minus one of these elements will be bigger than the target number. So we know the target number, so we can basically search for the right value among these elements. And then for each element, we can also store the place in the array where this element is. And essentially, we are looking through all the elements to the left of the current considered element. And we first need to find all the elements this sufficiently big sufficiently big sum. So can we solve this as a monotonic stack over a prefix sum? Let me just so for any element of the prefix sum, we only need to store the most beneficial elements from the left So if there is some less beneficial element farther to the left, we don't need to store it anymore, right? And then we can do a binary search in this range to find the closest element that will be sufficient to get to our sum. Okay, so what I'm trying to say, let's actually do a simpler thing right now. And let's do this because I think it will not change for the negative numbers at all. So the target is 5. Maybe let's do a target of 7 and do something like this, which will be more interesting because then we will get 7 from these two numbers, but we will also get it from these two numbers, and having two numbers is better. So we just do, the answer will be 2, and now the prefix sum will be 1, 3, 6, 8, 14, 15. So now what do? We move from the left to the right and consider each element. So for each element, we are keeping a stack, monotonic stack, which will be I think I will need to add a negative number here just for the sake of it. So let me do 3 and then -2. And then 2 plus 3 plus 2. Yeah, we will also consider this sequence of number as a suitable one, and then this sequence of number as a suitable one, and then finally this will be the correct sequence of numbers. Okay, good. So the only thing that changes is that now we have 3 as on the first place of our monotonic stack, and then we have -1, etc, etc, etc. So why do we need that? So that we have prefix sum that sometimes grows, sometimes shrinks, and then we keep our monotonic stack. So what do we keep there? We need to keep basically the smallest number. So it will be monotonically increasing, because okay, so we first put 3, right? And then let's say we move on and consider 1. So if we put this monotonic 1 on the monotonic stack, then when we will be considering some other value, right? Do we need to consider this 3? No, because 1 is closer, and we also store like not only 3 but 3 at index 0 and 1 at index 1, right? And we will be subtracting this from our prefix sum to get to the sum for whichever number we are considering. So we can only subtract more if this number is bigger, and we will this number is also farther away, so we never need to consider this number at all. So whenever this will be basically monotonically increasing stack. And then when we are considering other numbers, we will check. We will start binary search. Okay, so first one and 1, we are adding this. We have considered at this point we don't have any numbers such that we can achieve 7. So what do we need to achieve 7? We need to have -6 on the left here, right? So we can do binary search over our monotonic stack and see if there is a -6 in there. And there is no -6, so we cannot achieve -6 or smaller number, right? So the first one that is smaller or equal to -6. Given that we don't have this number, we will be just adding this number to monotonically increasing stack. Now we get to this 3, and we consider 3 and 2, right? So now for 3, we need to find -4 to the left. We don't find it. We continue. We consider 6, right? So we consider 6 at 3, and we need to find -1 somewhere on the left. We don't find it on the monotonic stack to the left, so we just append it. And at this point, this is still correct, right? Because we are still not getting 7. And this is right. And then finally, we are considering 8 at 4. And for 8 at 4, we just need to find 1. And we can find 1 or smaller, right? So we, 20 minutes have passed, but I think we are doing good so far. So for 8, we need to find 1. We can find 1, so then we can do 4 minus 1 plus 1, right? How many total elements do we need to consider? But no, right? So it's a prefix sum that goes them. So what's the problem here, right? The elements contributing to this prefix sum to be like this can come from the left of this, right? So to achieve this, at this point, we need to consider all elements. How do we know here that we need to consider all elements? Oh, but it's correct, right? Yeah, it's correct. Whew. This is right because we we can just, we get the same thing from these 3 elements, so we never need to consider this. Yeah, we never need to consider these elements, so that's correct. We are only using these 3, and then we just need to do 4 and subtract 1 to get to how many elements do we need to formulate our answer. So then the answer is 3. And then we still updated and added to the monotonic stack because now it's even increased even further. And finally here we have 14. So we are considering 14 at number 5. And for 14, we now need to search through this monotonic stack to find 7, at least, at most 7, at most 7. So we find this 6, and then we do 5 minus 3, and then 2, and we update our best value. And then finally for 15, we consider 15 at number 6. And then for 15, we just need to find 8. And we find 8 here, and we do 6 minus 4, which is also 2, so it doesn't change anything. And yes, this is correct. So this solution, monotonically increasing stack on prefix sums, will be of n log n runtime and of n space. Yes, of n space. Let's implement this. I'm not sure if there is a linear solution, but I think log linear is also fine. So what do we do? Stack will be this. Then, okay, prefix sums will be this. And then for element. Okay. Current sum equals 0 for num in nums. Current sum plus or equal num, and prefix sum append current num or current sum. Okay, so for each of the elements we append to our current sum. This is good. Now we need to set up our binary search, and let's start with, okay, let's actually update and add stack here. And for our binary, we will also need to update the value of our smallest size of the subarray. So the smallest size, we will start with a float of infinity. What do we need to return if there is, if there is no such array? Return -1. Actually, let me do -1, 2, and the goal is 4. We need to return -1 just to keep track of our corner cases. Okay, so then for I and prefix I will call it pref in enumerate prefix sum. So for those two elements, what we will be doing, we will be first of all searching for the element on our stack that is smaller or equal to our to prefix sum target will be equal prefix sum minus k, right? So yeah, here we have 14, we need to subtract 7, yes, so prefix sum minus k. So this is the target. Now let's set up our binary search algorithm. Let's define that left will be -1 and right will be, no, let's actually, so I'm figuring out this corner case when there is no stack at all. If there is just one element on the stack, like -1 plus 0 divided by 2, I actually don't know what will be the result of this division. Is it dividing closer to 0? Like, I hope so. Okay, let's figure this out. So what we want to point our left element we want to point to the element smaller than, the invariant will be always the element smaller than the target, and R always bigger or equal than the target. So now we will need to consider if the stack is there, if the stack is not there. Okay, if stack, we'll only need to do that if stack. Let's first figure out what we will do if there is no stack. Or either way. Okay, so if the element that we want to add to the stack is smaller than what is already on the stack, so while stack and stack minus the last element of the stack and the 0th element of this is bigger than the prefix sum that we have right now. Oh no, it's pref, and target is prefix sum minus k. No, prefix sum here. Okay, I'm mixing this up myself. Probably a bad variable name. Let's call it current pref sum. Longer but clearer. So if stack is bigger, while stack is bigger than current prefix sum, we just do stack pop, and then stack append, and we append current prefix sum at the number of element I. Okay, so that's what we do for each of the elements. But now here we also need to do a loop to update whether we have found, whenever we find a suitable combination in our monotonic stack, we might need to update our smallest size. So here we are doing this binary search, and we want our left pointer to always point to the index that is smaller, to the index that we are searching, but it might not exist, so we need to point to the left by default, and then the right number will be always bigger or equal than our target, so it will always not work for us. So we can so if we just continue iterating, yeah, we should point to the number that is bigger than our stack, because we need to be able to point with left for this last element on the stack, and we will have the condition that left will all be smaller than the right. So we point left as -1 and right as length of stack. Now M will be L plus R minus L divided by 2. And can it get outside of the bounds for our array? Let me check, because this is the first time that I'm implementing binary search like this. So if L starts as -1 and R starts as, it can at least starts with 0, 1, -1 plus 1, so 0 will be middle ground, and then we can only move to the right. Okay, so it looks like it works. Please reestablish the connection already. Okay, let me reload the page. Cool. So while L is smaller than L plus 1 is smaller than R. So while they're not on the two positions near each other, M will be equal to this if current element, so stack at M, and we choose the zero element, so the prefix sum. If it's smaller than our target, then we can safely move left, so it will always be smaller. L will be equal to M. Else, if it's bigger or equal, then we can safely move R, so R will be equal to M. Then in the end, if L is not equal to -1, then it means that we have found an element that is like a suitable element in our monotonic stack. So in this case, we need to subtract. So position will be stack of at position L, and we will choose the first. So this is where we store the position. So previous position will be this. And now we need to update the smallest size will be minimum of the smallest. Sorry, minimum of the smallest size and position minus previous position. We don't need to do +1 here, as we have discovered when we went through our iterations. Okay, so this looks good. And we do this logarithmic loop in each scenario, and then we also update our stack down here below. And then finally we need to return smallest size if smallest size is not equal to float of infinity. And if it's still equal to float of infinity, then we need to return -1. Okay, looks good. I think I have cracked this, at least for of and log n space. Oh, sorry, runtime and of n space. Let's now quickly do a simple problem. So which one should we choose? This one will be too long to walk through, but let's maybe start walking through it, and then we will see if it works or not. So these are the numbers and the result that we want to get. And oh no, this one, right? And this is the prefix sum that we have for it. Okay, so now we have calculated the prefix sum. Let's just check. Okay, for num and nums, we are adding our number, and we are doing this starting at 0. So we are then appending the current sum. Looks good. Now stack is empty. Smallest size is equal to float of infinity, and for this we start and our target. So okay, so first of all, target for this prefix sum, the first prefix sum, we need to find 3 minus 7, so we are looking for -4. And there is no stack, so we just go here. And there is no stack, so we just go here, so we just append this to our stack. So we append that 3, 0 thing. Then we move on to maybe explicit, so we move on here. So now we do consider 1, and target becomes, for 1, it's 1 minus 7, so it's -6. And we see the stack, so we try to iterate over it. So -1 and R will be 2, and while L plus 1 is smaller than there. Okay, m will be 0. And if stack at this position, stack is 0 position, 0 position 3, right? Yes. Will be, it will be bigger than target. So we safely point R at this element of the stack. And then we get out of this loop. And L is equal to -1, so we are not updating our smallest size because we haven't found the element that we are looking for. Okay, so far so good. So now we are figuring out there is stack, and while stack, the last element on the stack, is bigger than current prefix sum. Is it bigger? Yes. Now we can just remove it. So we do stack pop, and then we update our current element, so it will be 1 at 1, right? Yes. Okay, and then we continue in this manner. I think so far it looks good. Binary search looks good. Returning the right value. So let me just check that I'm using the correct values everywhere and that I'm using my stack and my containers that I have created and updating the smaller size and that it's minimum. We are targeting the minimum amount of things and we have just spent 40 minutes on this. So let's just finish, see how it goes. And if it doesn't go well, what can you do? Output -1. Okay, so we are not processing well some of the corner cases. Output 1. Why is that? Oh yeah, I think I know why. I think I know why. So stack will be at, when we are considering the first element, the only element that we have. That was the corner case that we didn't think through. It should already have an element of like 0 in our stack. So stack will always start with, stack will never be empty. So we do 0 at -1, at position -1. Yep. Okay, so then here we will always have stack because we are always appending this, so we can just do this. This is strange. And here, okay, we are always outputting -1. So is it some? And here, let's try our own test case just to ensure. Oh, I see there is a message. Give me a second. Oh, sir, my today question is that I like coding and I use Linux. So what should I do between full stack dev or DevOps cloud engineering? I like coding and I use Linux system. So do you like using Linux system? DevOps is hard, but it's still just the same thing, kind of, as coding. It's just what do you prefer more? If you enjoy doing full stack, continue doing this. If you enjoy more DevOps, continue doing this. Probably if you are just starting, you can do both things and see what sticks. Basically, why would you even care that it's hard DevOps in entry level? So what exactly is hard? Is it hard to get into that? Yeah, there are just more full stack jobs than DevOps jobs. So it might be harder to get entry, but it also means that there is less competition. So these kinds of things are balancing out. But full stack is more general. Okay, if you like Linux more, do Linux more, then the smaller amount of jobs is balanced out by the smaller amount of people wanting to do those jobs. And also with the current AI landscape, we will still need people to support the systems and to make decisions when something goes wrong. So DevOps people will be a little bit more needed than full stack developers. But okay, I'm trying to predict the future. Right now, it's too hard. If you like Linux more, then do Linux. And let me get back to this problem. What the heck is going on? I wanted to add our own test case. So let's see that we are doing well for our own test case. So okay, so nums is this and k is 7. Let's see. Oh, I'm just calling it I. Yeah, I thought that I'm calling it position, but okay, here we are doing everything correctly. That's great. So our logic just doesn't work with these elements, which is strange. So what are we missing for when we need our first element? Oh, should we just add 0? No, we will be adding 0 for the first element, right? So it cannot be 2 zeros. Yeah, it should be -1 here, and it should be 0 here. This is basically the initial sum. So equal length of stack. Oh, are we actually incorrect here? Length of stack. So it should be pointing. So length of stack is 1. Oh no, yeah, it's pointing to -1, and this will be pointing to 1. Okay, this is still correct. Is it again some stupid mistake? Let's do print I current prefix sum and stack. Let's print L and R here. Oh, so why are we not finding? Oh, but we can be equal to target. That's the corner case. Yeah, I was again saying the right thing, implementing it correctly. If we have something that is equal to our target, then we are still fine. Okay, so mostly correct implementation now. Should be. Yeah, but there is a linear approach, freaking linear approach. How do you do this linearly? I have no idea. I will be researching this offline. I don't know. I think my solution was pretty clever. And I solved a hard problem, making a stupid mistake again. But I will end it here. And I will see everyone a little bit later today, actually, to stream the machine learning system design instead of ML coding. not ML, just coding. Yep, so I plan to do that since I have more time. I just spent 50 minutes on this problem today. Okay, thank you everyone.